This is the first lecture of Chapter 18, and in this chapter we will be looking at a different type of reactions. Remember, we've looked at substitution reaction, elimination reaction, reduction, oxidation. This chapter deals with pericyclic reactions. So, in this lecture, first we will look at and define conjugated double bonds because they play an integral part in these reactions. Then next we will define pericyclic reactions and give some types of pericyclic reactions. We'll discover that there are three types. In this lecture, however, we'll concentrate on one type, which is known as the cycloaddition. So we'll have to define the cycloaddition and discuss it and apply those to this type of reactions. So let us begin. First, conjugated systems. What are conjugated systems? Conjugated systems consist of alternating double bonds. So here's an example, isoprene. For example, isoprene has a double bond here, a single bond, and a double bond. So they're alternating double, single, double, single. Here's another one, 1,3-butadiene, double, single, double. 1,3,5-hexatriene, double bond here, single bond, a double bond, a single, and a double. And a last example is 1,3-cyclohexadiene. So we have a double, single, and a double. Notice that if we put a double bond here, that would be benzene. And that's no longer alternating because we know that the bonds in benzene, they're all equal. So that's a unique molecule. And that's why it's under a special category called aromatic molecules. Let us look here at the importance of conjugated systems in nature. They are found in nature, widely found in nature. And here's an example. And this is here beta-carotene, as we have seen here in this example. Notice that it has a lot of alternating double and single bonds, as shown here. And of course, that gives its highly colored observation. So it's highly colored. So conjugated double bonds are typically highly colored compounds, or should I say compounds that have conjugated double bonds are typically highly colored compounds. Okay, let us look at energy of reactions. What's so special about compounds that contain conjugated double bonds? They're more stable. But let us design an experiment to prove and demonstrate that they are in fact more stable. So let us look at what's shown here. So here we have a 1,3-butadiene. So this one has a conjugated system. Notice this is conjugated. Here is another isomer where we have here a double bond, but these are not conjugated because here's a double bond, here is a single bond, here's a single bond, and a double bond. So they're not conjugated. If we should carry out a reaction in the presence of hydrogen and a catalyst, so it's a hydrogenation, it's an exothermic reaction. It gives the product here pentane, both give the same product, pentane. You can see here it's an exothermic reaction because heat is given off. But you'll notice, however, that we have more heat given off here than here. So more heat is given off for the system that's not conjugated, and less heat is given off for the system that is conjugated. So for the exothermic reaction, we can in fact use an energy profile to show this concept. So here we have a double bond that's isolated and another double bond or system that's conjugated. The more stable system will give off the least amount of heat, whereas the less stable system will give off more heat. You may recall that in a energy profile diagram of this type, anything that's in this region or lower in the region is more stable than anything that's higher in that region. So we can tell from this that conjugated double bonds are more stable, or systems or molecules that have conjugated double bonds are more stable than molecules that have isolated double bonds. Let's see how that works in terms of the stability. So here we have the same molecule here, but the free movement of electrons across the carbon skeleton, that is what gives this molecule its stability, or should I say that contributes a lot to its stability. The free movement of the pi electrons here. So as you can see, it's very difficult to draw the movement of electrons. So we know that this carbon here is sp2 hybridized with a p orbital here with one electron. Same here, and here. So these electrons can freely move. So it's very difficult to draw electrons moving. So here's another way of representing that concept. We can put dotted lines to show that these electrons are freely moving across the carbon skeleton. That's of course very difficult to draw also, because we got to draw all the p orbitals. Another representation that's typically used in organic chemistry and that we are very familiar with is that of resonance structures. So here are the resonance structures that illustrate the electron movement by using arrows to indicate these movements. So here's one. So these electrons can come out of this carbon. Here they are. And what's left behind is a positive charge. And then these electrons here can come out to bond right here. And what's left behind is a positive charge. So this is another way of representing the free movement of electrons across these carbons here in a conjugated system. So now you can see the importance of resonance, or one of the importance of resonance. So let us look at a consequence of this. So here's 1,3-pentadiene. Conjugated system. Again, you have to be able to recognize conjugated systems because they're unique in organic chemistry. So if we have a 1,3 conjugated system here and react it with bromine, if it's a regular addition reaction, we'd expect it to add right across here because that's a double bond, or right across here because that's a double bond. But what's observed is we have a molecule like this where it adds here and here. And of course, if you draw the resonance structures, you can see why it adds at these points, because of the free movement of these electrons across these four atoms. So here's another product where the bromine can add here and the hydrogen can add here. So again, conjugated systems are unique in that the electrons, there's a free flow of electrons across the carbon framework. Same applies for electrons that's on a heteroatom. So here we have oxygen. Of course, as you know, oxygen has two pairs of unshared electrons. So here's your conjugated system here, and here's a pair of electrons. So these electrons can conjugate or freely flow across these other carbons. And how do we demonstrate that? We demonstrate that by resonance. So here's the arrow showing that these electrons can bond here, and then these electrons come out here, and here they are. And of course, if we move electrons from a neutral atom, it becomes positive. These electrons again can move here and eventually end up here, and of course it becomes a negative charge, or an anion. So again, the bottom line is that these electrons can be delocalized to this carbon as shown here, and to this carbon as shown here. Free movement of electrons provides stability to a molecule. Here are a couple examples that are natural products. Curcumin, that's a spice, and of course, as you can see, here is a pair of electrons. So these are delocalized all the way over to here, or can be delocalized through the benzene ring all the way over to here. Same here, OH. Another example, this is a dye that we'll see when we look at the last chapter on proteins. So here are some electrons, two pairs of electrons. So these can be delocalized all the way over to here. So we can show resonance structures here, and there's a delocalization or the movement of electrons across the carbon skeleton or the atomic skeleton of a molecule. That gives stability to a molecule. Okay, let's see how we can apply that. So now let's look at pericyclic reactions. Definition: pericyclic reactions involve conjugated systems. So again, we will have to be able to recognize a conjugated system and determine if it can participate in the pericyclic reactions or not. So pericyclic reactions involve conjugated systems in which electrons of the pi and sigma bonds are transformed into new bonds. Okay, so the pi bond, which is adjacent to the sigma bond, or the double bond adjacent to the single bond, they're now transformed into new bonds. Typically, the transition state is cyclic. That's why it's called pericyclic reactions. So this is a new type reaction, pericyclic reactions, which deals with conjugated systems where pi and sigma bonds are transformed into new bonds. There are three types of pericyclic reactions. One is the cycloaddition, which we'll concentrate on in this lecture. Then we'll have the electrocyclic reaction, and we have a sigmatropic reaction. So we'll define those in the next lecture, but in this lecture we'll concentrate on the cycloaddition reaction. So here's some examples. So the cycloaddition reaction, as you can imagine, cycloaddition. So you can see here we have a double bond, and here is our conjugated system. And since it's a cycloaddition, we're adding these two together to get a cyclic system. Here it's, in this case, it's a cyclohexene. Electrocyclic reaction, here's our conjugated system. As you can see here, it closes up to form a cyclobutene. That's again pericyclic reaction. Here's one that's a little different, a sigmatropic reaction. And here we have this is not conjugated, but we have two pi bonds. And notice what's happening here in the presence of energy. This pi bond here, this sigma bond here, moves over to here, as you can see here. But we will emphasize that in the next lecture and look at reactions and how that actually happens. But for today's lecture, we will concentrate on cycloaddition. So let's begin. The simplest, of course, is two ethylene units. So here is ethylene and here is cis-2-butene. Notice again, here's a double bond, here's a double bond. This is not conjugated because we're looking at the simplest system first. So here is a double bond and a double bond in the presence of light. Okay, this is key because we'll emphasize that in a second. In the presence of light, we have a product here. And this is cis-1,2-dimethyl-cyclobutane. So it's a cycloaddition where these two molecules add together to make a cyclic structure in the presence of light. These reactions, we describe them as stereospecific because you can hear this is cis-butene, and over here there's a cis relationship here. This is trans-butene, as you know, trans across the double bond, and over here we have our trans product. So they're stereospecific, where we have a specific stereochemistry in one of the reactant, and it gives a specific stereochemistry in the product. So those are stereospecific reactions. They're also described as 2 plus 2. Of course, as you know, in chemistry, we always come up with shortened form of representing different concepts when we communicate. So oftentimes, we refer to these reactions as 2 plus 2 cycloaddition. Why 2 plus 2? 2 pi electrons, 2 pi electrons. So that's why it's a 2 plus 2. Let us see how this reaction work, or these reactions, how they work. In this case, we won't have a reaction mechanism because it's a one-step reaction. It takes place in one step. So let us try to use a different approach to understand how these reactions work. So to explain these reactions, first, let us look at the formation of two molecular orbitals from the pi bonds. Okay, so if there are two molecular orbitals that are formed from the two atomic pi bonds, we have shown here. So for reactant 1, here is molecular orbital 1, that's represented like this, and here is molecular orbital 2, that's represented like this. We can call them pi 1 and pi 2 star. But notice these are molecular orbitals. That's where the electrons go in to form bonds. Again, to differentiate between these two, one is lower in energy and the other one is higher in energy. So notice the energy is going in this direction. So anything that's low here is low in energy, and anything that's high here is higher in energy. So for these two molecular orbitals, one is lower in energy, pi 1, and the other one is higher in energy, pi 2 star. To differentiate between these two, you will see here that we have colored here the top part of these pi bonds, and we have reversed it. That's just to show that there is a difference. So in some books you'll see plus here and minus and plus and minus, and then here we have plus and minus and then plus and minus, just to show that they are different. They're not the same. They're different, and the only difference is that they have different energies. So for reactant 1, which is our ethylene, and for reactant 2, which is our butene, the same pi bond occurs, and we have two molecular orbitals. Key here, though, we'll introduce some terms. Here is HOMO, homo, or the highest, let's see, we got it up here, the highest occupied molecular orbital. Highest occupied. Why occupied? Because the two bonding electrons are in this orbital. The lowest unoccupied molecular orbital, of course unoccupied, so there are no electrons here. So here is the LUMO, and here's the HOMO. Same for the other reactant molecule. We have the HOMO with 2 electrons, and we have the LUMO with no electrons. For the reaction to occur, electrons must move from the one reactant, HOMO, into the LUMO of the other one. However, as we'll see in the next slide here, is that there has to be, the phase must be correct. So here is the LUMO of one reactant, and here's the HOMO of the other reactant. You will see here that the phases are incorrect for a reaction to occur. So we say that this is symmetry forbidden. So a reaction will not just occur by having electrons flow from one reactant HOMO to the LUMO of the next reactant, because the phase must be correct. How do we make the phase correct? What you can do is look at one of the molecules. Let's look at ethene, for example. And here's the HOMO. Here are the 2 electrons in the HOMO. Here's the LUMO, no electrons. In the presence of energy, in this case light, of a specific wavelength, an electron will be promoted from the HOMO into the LUMO. So this now becomes the HOMO. So once again, so the reaction will not typically occur in terms of electrons flowing from the HOMO to the LUMO, because as we've seen from the previous slide, the orbitals are not in the same phase. We say it's symmetry forbidden. But if we should expose one of these molecules to light of a specific wavelength, there is a promotion. So we say it's an excited molecule. So this now becomes the HOMO. Notice again the orientation of the orbitals here. So the next slide shows that the HOMO of one molecule and the LUMO of another molecule, now the phase are correct. There's a correct phase, and this is symmetry allowed. So the electrons will flow from the HOMO of one molecule to the LUMO of the other one, and we have symmetry allowed for that reaction to occur. The key, however, is that we must supply energy in the form of light of a specific wavelength to convert the HOMO of one of the molecules to the LUMO by excitation, taking one electron from the HOMO into the LUMO to create a new LUMO, a new HOMO. Okay, so the application of this is, if we have ethylene and cis-butene, 2-butene, energy, in this case this is light, as we've shown from before, of a specific wavelength. You need not put the specific wavelength, just put light. The electrons start to flow, create a bond right here, a diradical is produced, and of course this closes up to give the product. Same here. Notice the stereochemistry. This is the cis, so it remains cis, and the product is cis. Let's look at this other one, the trans. Supply energy in the form of light. It could be H nu or just light. The electrons start to flow from the HOMO to the LUMO, because we have now excited one of these molecules, and we have a bond here, and eventually we have the product over here. Notice again, trans gives the trans intermediate here and the trans product. So examples of the 2+2 cycloaddition. So here we have the alkene, and here we have the alkene, or the double bond. In the presence of light, we'll have a bond here, cycloaddition. Remember, it's a cycloaddition, So we'll have a ring formed here, four-membered ring. So here's that four-membered ring. The double bonds here, one way of writing it is that this double bond comes out to form that bond, and this comes out to form this bond here. So here we have this four-membered ring. Here's another example. Double bond here and double bond here, and we form our four-membered ring here. And the last example here, here is our double bond right here. Here's a double bond right here. So a bond will form right here, and this is it. And of course, we have the ketone. So it's a cyclobutanone. So as you can see, these reactions are very important in organic chemistry to form cyclic compounds. Key, if it's a 2 plus 2, we'll need light for that reaction to occur, or for these 2 plus 2 pericyclic cycloaddition reactions to occur. Okay, let's look at another type reaction of the cycloaddition. This is the 4 plus 2. And you should not be surprised here of what the 4 and the 2 means. It means that we have a system that has 4 pi electrons and a system that has 2 pi electrons. So 4 plus 2. Energy. We'll see in a second if this energy is heat or light. This reaction is very important in organic chemistry, and it was discovered by Otto Diels and Kurt Alder, German chemists, and they actually got the Nobel Prize for this discovery. It is very important because, as you can see here, it makes a cyclohexene. And as you know, in nature, a large percentage of organic compounds are 6-membered rings. So this gives a way of making 6-membered rings by a cycloaddition, 4 plus 2 cycloaddition. So a lot of times we will refer to this 4 plus 2 as our Diels-Alder reaction. Okay, here is a brief mechanism of the reaction. So we have electrons coming out to form this bond here, and electrons coming in to form this bond here. These electrons form the double bond here, and form the cyclohexene, as we have seen here. This is the transition state, usually a little double dagger right here to indicate transition states. You can see a cyclic transition state here. And of course it forms the 6-membered cyclohexene. Key here is it's also stereospecific, because if we have this stereochemistry here in which they're on the outside of the double bonds here, it's going to be on the same outside of the 6-membered ring. So again, remember, stereospecific reaction is you have a reactant with a specific stereochemistry and gives a product with a specific stereochemistry. So for these reactions, you would have to be extremely careful to include the stereochemistry for these reactions. Let us see what's needed for this reaction. Is it heat or is it light? Here are the ground state molecular orbitals of 1,3-butadiene. Remember, we have now 2 double bonds. So we have a double bond here and a double bond here. But to represent all these orbitals, we have 4 molecular orbitals, as shown here. And to differentiate them, we have to alternate the colors so that they are all different. So notice for this one, all the shaded are down. For this one, 2 are shaded down and 2 are up. And here we have 1 down, 2 up, and 1 down. And we alternate here, up, down, up, down, up. So these are 4 different orbitals for butadiene. Another way we can represent them is pi 1, pi 2, pi 3, pi 4. As you can see here, there are 4 electrons. So we have 2 electrons in pi 1 and 2 electrons in pi 2. This would be the HOMO for our butadiene, because that's the highest occupied molecular orbital. This would be the LUMO, or the lowest unoccupied molecular orbital. What I want you to concentrate on is the phasing here. Let's look at the other reactant, ethylene. Only 2 molecular orbitals, because there's just 1 double bond. So here we have the HOMO and the LUMO. The HOMO, of course, has this. So, for reaction to occur, the electrons must transfer from or move from the HOMO of one reactant to the LUMO of the other one, or the HOMO of one to the LUMO of the other one. So what we need to make sure of, though, is that it's symmetry allowed. So let's look at this. So here is the HOMO of ethylene. Notice these two are up. And here is the LUMO of butadiene. Notice these two are down. Another analysis we can use is the HOMO of butadiene. Notice this is down and that's up here. So this is shaded, unshaded. And the LUMO here, this is unshaded and that's shaded. So let's see if it's symmetry allowed. As we can see here, the LUMO of ethylene, or the lowest unoccupied, looks like this, and the HOMO of butadiene looks like this. So we can see here shaded, shaded, and unshaded, unshaded. So the phase is correct here, the phase is correct here. So this is symmetry allowed. So we need not excite any one of these molecules. We need not use any light of a specific wavelength. It will just go. They typically go, however, at elevated temperature. We just have to apply heat. So for these reactions, here are some examples here of the Diels-Alder 4+2 cycloaddition. What we have here is, here's we call this the diene, and here is the the double bond. I should really write this out. So this is called the diene, D-I-E-N-E, and this is the dienophile. So again, as you know, in chemistry we use terms just to communicate. This is a diene, as indicated here, 2 enes, 1, 2. And this is the dienophile. Let's analyze that word. This is the phile, which means loving. So it loves the diene. So the diene and the dienophile, they work together well for a reaction to give this cyclic product here. So notice the bond will form here and here, and of course the double bond moves into that position. Here's another example. Here's the diene, and here's a dienophile. Dienophile is right here, so the bond will be right here. So here's the new bond. Here's a new bond here, sigma bond. And notice the stereochemistry. These are on the same side, so we have the same side here, or the cis product. Let's look at this as the last example. Here is cyclopentadiene, but it's a diene and it's conjugated. So here's the dienophile over here. So you can imagine a bond will be made from here to here and from here to here. So this is a bridge. So here's the bridge. And here is our 6-membered ring right here. That's formed. So again, and notice again, let me point out, it's done in the presence of heat and not light. So conclusion, if there is a Diels-Alder reaction or a 4 plus 2, it's carried out in the presence of heat. And of course, as we've seen from the previous slide, if it's a 2 plus 2 cycloaddition, it's carried out in the presence of heat, and of light and not heat. Let me say that again, just in case I mix the terms up. So the Diels-Alder reaction, which is a 4 plus 2, is carried out in the presence of heat. And for the previous reaction we discussed, the 2 plus 2 cycloaddition is carried out in the presence of light. Well, that's the end of this presentation. So once again, take your time and read through your text as you go through these slides. I'll post the slides so you can take your time in working through this lecture here. As you watch the video, you can pause it and just take notes and write down these different concepts and try to understand it. It's a new concept, so it's going to take a little time just to make sure that we understand it and to be able to apply it. So once again, we are here to learn not only the facts and the concepts, but equally important is to apply these concepts to solving problems. So continue to study hard, and I will have more information for you on our D2L.